So we're beginning our last chapter here this morning, and this last chapter is over nuclear chemistry. And I'm going to warn you, this is kind of nuclear chemistry is going to feel a lot more like a Chem 105 kind of topic, in the sense that we're not going to go deep on any particular topic. We're just going to kind of bounce from little idea to little idea to little idea. And we're going to kind of stitch all those little ideas together to get at least a modest understanding of nuclear chemistry overall. So we're going to speak into each of these 6 categories today. For the most part, we're going to focus mostly on these first 3 this morning, which is also the majority of the quote-unquote work for that. And also for that reason, if you want to think about, like, in terms of homework, there's only one assignment here in chapter 19. The 19 review is going to have a hodgepodge of some other things that we talk about tomorrow in it, but there's not really enough there as far as what we're talking about tomorrow to warrant an entire second assignment. And so I'm just going to stick some review questions of that kind into the review. But we're going to spend mostly today talking about what radioactivity is, what it means to be a stable nucleus versus an unstable nucleus, and a little bit about kind of the energy that comes along with some nuclear reactions. And then tomorrow we'll get into talking about more application-oriented kinds of things. What kinds of nuclear reactions happen in our world? How do elements get formed from nucleosynthesis, both natural nucleosynthesis and synthetic nucleosynthesis? And what are some general hazards and uses for radioactivity, many of which we're already familiar with? So let's kind of go back to the beginning here. Of the fields of chemistry, nuclear chemistry is one of the youngest fields. Nuclear chemistry inadvertently spawned quantum mechanics, not because they are directly related, but because some of the outgrowings of radioactivity helped to spur some of the great quantum mechanical questions and answers of the early 1900s, things like the gold foil experiment or Thomson's cathode ray tube experiment. The discovery of radioactivity is largely attributed to the French chemist and physicist Henri Becquerel. He's largely credited for being the first to discover radioactivity, although there were others that were working on it at the time. And while Becquerel is kind of famous or infamous for this discovery, and also for what this discovery ultimately did to him, you can see 1896, he is credited with detecting it. 1908, he's no longer there to take credit for it. He and again, there are probably more famous people that came out of his lab, Pierre and Marie Curie. Madame Curie went on to a much longer career, although radiation also ended up being what ended her life far too early as well. So what is radioactivity? Radioactivity, by definition, is the spontaneous emission of particles from some kind of a nucleus due to instability of that nucleus. Now, along with those particles, we usually do get radiation as well, energy. And so usually radioactivity has that pairing with it, where we've got this ejection of a particle, and with that particle usually comes some kind of energy transmission as well. Now, where we want to be really careful about nuclear chemistry, and this is where It is a departure from basically everything else that we've talked about for the entire year here, going back to Chem 1. In chemical reactions, we've always focused on the idea and concept of atoms and electrons rearranging themselves. So to get a new compound, to get a chemical reaction, we see these atoms moving around, or we see electrons moving from one thing to another if the reaction is a redox reaction. In nuclear reactions, we don't see that. What we see instead are the nucleons, the protons and neutrons that are being rearranged to form new elements or new isotopes. A completely different kind of look at, well, everything. Everything we've told you up until this point has been ignore the nucleus, focus on the electrons. The electrons are what are going to be forming the new bonds. Now we're telling you, ignore the electrons, focus only on the nucleus. That is the primary difference between a chemical reaction and a nuclear reaction. Chemical reactions focus on electrons and the rearrangement of atoms through different kinds of bonding. Nuclear reactions focus on the nucleus, nucleons, protons and neutrons. And whereas chemical reactions were obeying the law of conservation of matter, or the law of conservation of mass, there's a version of that in nuclear chemistry as well. The number of protons and neutrons need to remain the same throughout a nuclear transformation. Nuclear equations are used to account for this balance of mass. Now, we're going to say this second statement with a little bit of asterisks on it. And the reason is, in nuclear reactions, the total number of protons and neutrons will remain the same. But the individual number of protons and neutrons may not necessarily remain the same. And when we start talking about different kinds of nuclear reactions, that distinction that I'm making here will make more sense to us. So we are talking about nuclear conservation, not necessarily subatomic particle conservation. Now, when it comes to radiation, there are primarily 4 or 5 known types, and they fall into a couple of main categories. Nuclear transmutation is the process by which this happens, though. So when we are describing nuclear transmutation, what we are describing is the transition from one isotopic form to another. Now, why does it do this? Well, the primary reason that any of these nuclear decays happen is because of stability. The great driving force of all chemistry, regardless of subfield, is stability. Everything is seeking to achieve a greater, more stable state than what it was before. Exothermic reactions take place because the products are at a higher stability than the reactants were. Nuclear reactions take place because we are at a higher stability as product nuclei than we were as parent or starting nuclei. In these transmutation reactions, what we see is that we have a disintegrating nucleus. The nucleus is literally falling apart and destroying itself in the name of stability. It was less stable before, and now it is more stable. But what we have to understand about radioactive decays, these nuclear processes, is that stability is not necessarily stable. In a nuclear process, the product is going to be more stable than the reactants, but that doesn't mean it qualifies under the definition of what we would call stable. A stable nucleus won't decay at all. Carbon-12, for example, is a stable nucleus. It does not decay into anything else. It has no reason to. Carbon-12 is a perfectly stable isotope. But carbon-13 and carbon-14, which have different numbers of neutrons compared to those 6 protons, they are not stable. And because of that lack of stability, they are going to disintegrate. They are going to fall in order to create something that is more stable. And that process is going to go on until we get to a stable isotope that does not want to decay at all. So there are multiple forms of nuclear decay. The first and probably the most common, or at least the most commonly known, is alpha decay, alpha radiation. What happens here is a heavy nucleus will eject an alpha particle. An alpha particle is essentially a helium nucleus. So 2 protons, 2 neutrons, no electrons. And in this process of alpha decay, we end up with a lighter isotope. 4 particles have been ejected from the nucleus. We see a change in the atomic number by 2. We see a change in the mass number by 4. So that's alpha decay. In beta decay, there are 3 subphases of it. But they all have kind of the same look and feel to them. So the 3 subsets are what are called negatron radiation, or negative beta, positron radiation, or positive beta, and electron capture radiation, where a nucleus literally grabs a core electron from the electron cloud. And in that process, the electron reacts with a proton and turns it into a neutron, basically. But they all have a similar kind of appearance. Beta decay is given by the Greek lowercase letter beta. So it looks like an uppercase B with a tail here on the bottom. Beta decay involves no change in mass, but a change in nuclear charge. So in negative beta radiation, what we'll see is that a negative beta particle is ejected. In positron radiation, what we'll see is a positron, or a positive beta, is ejected. In an electron capture, what we'll see is that an electron is added to the reactants before they convert to product. And what we'll also see when we look at these a little bit more closely is that two of these actually have the same effect on the nucleus. It's just the mechanism by which they change the nucleus that we have to look at. Is it coming through ejection of a particle, or is it coming through the absorption of an electron? So pictorially, this is what negative beta looks like. We can think of negative beta as being like an electron. Again, no charge, -1, no mass, -1 charge. Chapter 2, that was effectively what we described an electron as. Now, with these nuclear decay reactions, one thing that we want to kind of take a look at is we need to start thinking about neutrons as being more than just a single particle. Now, if you've followed anything that has been happening with the CERN Super Collider over the past decade plus in Switzerland, or even if you've watched popular TV shows like The Big Bang Theory or something like that, you've probably heard some of references to some of these subatomic particles, bosons, quarks, the Higgs boson, muons, and so on. What we know about subatomic particles is continuing to evolve. But what we need to understand is that, in particular, protons and neutrons are made up of smaller subatomic particles as well. And for the purposes of trying to understand what's happening in these beta decays, what we really need to think about is, well, what is a neutron? We know a neutron is neutral in charge, right? Well, why is it neutral in charge? Well, the reason we think that the neutron is neutral in charge is because we think that it's comprised of subatomic particles that are positive and negative. And so what negatron radiation is effectively saying is that the neutron is going to lose its negative subatomic particle, and the thing that'll be left behind will be the proton. So in negatron emission, that's what we're saying is happening. We're basically turning one of these neutrons into a proton in the process of ejecting that negative particle. In addition to ejecting that negative particle, we also eject energy, as well as generating that proton out of that neutron. With positive beta decay or positron emission, we can see kind of the same thing happening, but in reverse. The positron is ejecting its positive subatomic particle. And since the positive charge is now leaving the proton, what we have left is a neutron. With electron capture, what we see instead is we see electrons being absorbed basically by the nucleus and into the overall fold of the nucleus. In that process, basically we have what's happening here in reverse. Instead of ejecting the positive to become neutral, the positive and the negative annihilate, and we get a neutron as a result that way. The fifth type of radiation, the third category, is something called gamma. Gamma radiation takes place when we have nuclear excited states relaxing. So we talked about the idea in chapter 3 in Chem 105 about electrons having excited states. Atom absorbs energy, electrons jump up, they relax back down to their ground state, it emits energy when they do so. Well, nuclei can do this as well. If we enter a nuclear excited state, when it comes back down to the ground state, the result is an emission of energy. That energy comes off in the form of gamma radiation. There is usually not a particle that is associated with gamma radiation. It's usually just pure energy. So how do we keep track of all of this? Well, the way that we keep track of everything is through something called a transmutation reaction. And what a transmutation reaction does is it allows us to track the scope of the reaction as we go from the parent nucleus, that is the nucleus as part of the reactants, into what are called daughter nuclei, that is the products. Now, made mention of this before, it's worth kind of reiterating here. Conservation law, as far as nuclear reactions are concerned, is not quite the same as what we saw with chemical reactions. In chemical reactions, we were concerned with, okay, I've got one aluminum over here and one aluminum over here. I've got two chlorines over here, but three chlorines over here. I'm going to need to add coefficients to balance it out. Or in the case of electrochemistry, I put the two half reactions together, but I see I have an electron left over. How do I make it so that the electrons balance out as well? In nuclear reactions, we're going to focus on two different ideas. Atomic number, representing the total amount of charge through the charged protons, and mass number. Mass number, again, just to remind you, being the total number of protons plus neutrons. Those are the things that we're going to seek to conserve in these balanced equations. And easiest way to get into these is just to do a bunch of examples and try to get something to kind of stick as we're going through them continuously. So, for example, polonium-218, it undergoes both an alpha decay and a beta decay. Now, for beta decay, for most problems, we can assume that it is talking about beta minus. So by default, if you hear something referred to as beta decay and it's not specific, assume that we're talking about the negatron emission. Otherwise, they're usually called by name. So positron emission is far more commonly used than beta plus. Electron capture is usually called out by name as opposed to just being called beta decay. But we're asked to look at these nuclear equations and describe these nuclear reactions under these two different types of decay. And so this is where we're going to need a periodic table, and we're going to have to remember what this means. So when we see references to something along these lines, we have to remember that this number refers to the mass number. The mass number is the number of protons plus the number of neutrons. So as we're writing this out, polonium-218 is the reactant here. I go to the periodic table, I see that polonium is element number 84. So this is where I'm starting. Now, if this were to undergo an alpha decay, then we have to go, okay, well, what is an alpha particle? An alpha particle is a helium nucleus, mass of 4, 2 protons, the question becomes, okay, well, after this ejection, what is left? Again, this is where I'm going to point you to the idea. This is way, way easier. Don't overcomplicate this. This is subtraction. If I have 218 nucleons and I lose 4 of them, this is going to sound like a second grade problem I give to my homeschool kids. Yeah, there's 214 left. And I have 84 protons and I've lost 2 of them. That means that there are 82 left. I go to my periodic table. I see that 82 is lead, Pb. And there we go. That's it. There is your balanced equation for the alpha decay of polonium-218. Now, to answer the question of, is that a stable nucleus? Well, this is where we can go to our periodic table again and look at it and say, okay, well, what is the atomic mass of lead? The atomic mass of lead is 207. This one's 214. Periodic table tells us roughly where we would expect stable nuclei. We're not there yet. Chances are pretty good this lead is going to undergo some kind of other kind of decay on its path towards stability. It's not there yet. But certainly a lot better than it was, because polonium, regardless of isotope, is radioactive, whereas lead at least does have some isotopes that aren't. Okay, now what about the beta decay? So starting from the same base, if this is a negatron decay, kind of your traditional beta decay, then the beta particle would be that. And so we lost no mass, so 218 would be the mass number. Now here's where we're going to be a little bit tricky. We've lost -1 charge. 84 minus -1 is 85. What we have to remember is that the two numbers on this side of the equation have to add up to this side of the equation. We go to element number 85. Element number 85 is astatine, AT. Its most stable its most well-known isotope has a mass of 210. So again, we're not there yet. This astatine is going to be radioactive, and that's kind of not a surprise because astatine is always radioactive. Now, if we were asked about other kinds of beta decay, we could look at them individually here. Okay, so what if we were asking about positron? Well, all that would change is the beta particle would go from -1 to +1. We would now need 83 to balance it out instead of 85. Element 83 is bismuth. If we went through electron capture, the third type of decay, we would still get 83, or excuse me, 218 as the mass number, because 218 plus 0 is still 218. 84 minus 1 means 83 on this side, so that means 83 on this side as well. So the resulting particle for positron emission and electron capture is the same. How do I know which one is which? How do I know which one happened? Radiation. I'd be able to detect the ejection of that particle or the loss of the electron. All right, any questions here? All right, let's do another one. We've got radon 222 decaying with a loss of 1 alpha. What is the balanced equation for this decay? So we set it up, the same way. 222 radon is Rn. Atomic number for radon is 86. We're losing 1 alpha particle. So 4, 2 alpha. 222 minus 4 is 218. 86 minus 2 is 84. Element number 84 is polonium. Second example here. Determine the product nuclide formed by the beta decay of tritium. Now, important side note here. Most isotopes of given elements carry just the name of that element. When it comes to hydrogen, hydrogen's 3 isotopes carry different names. So we're already familiar with H1. We've referred to this from the beginning as just simply hydrogen. Deuterium, H2, is the well-known isotope of hydrogen where we've got a proton and a neutron in that nucleus. Called deuterium because the Latin root deutero, or deuter, meaning 2. in organic chemistry becomes a much more important kind of isotope, and is used quite often in solvents. And the main reason is nuclear magnetic resonance works only on um, on isotopes that have an odd mass number. So if I have an organic solvent that is normal, all of the solvent peaks for those hydrogens would all show up. Deuterium works in helping this way because, well, if we replace the hydrogen 1s with hydrogen 2s, the hydrogen 2s would not be picked up by NMR. And so you'd be able to see what's in the sample a lot more cleanly because it wouldn't have all of the noise of all of the hydrogens from the sample. This is also where the term heavy water comes from. If you've ever heard of heavy water is deuterated water, where instead of H2O, where the hydrogens are normal hydrogen, H1, the hydrogen 1s have been replaced with deuterium, hydrogen 2. And in addition to making the water heavier, it also has different properties spectroscopically. And then lastly, H3 is tritium. And again, the origin of that tri for 3. Tritium becomes a lot more noticeable and recognizable in stars. Deuterium and tritium are a lot more common in solar objects, in space objects, and this is actually one of the driving forces behind some of the nuclear fusion that we see happening in the center of stars as well. So all that to get back on topic here, we want the beta decay of tritium. So tritium is mass number 3, atomic number 1 for hydrogen. And if we're undergoing beta decay, and again, we're assuming that this is talking about the beta negative. Three minus 0 is 3. 1 minus negative 1 is 2. We end up getting a helium nucleus here. Now, normal helium is helium-4. This is helium-3. So this helium is a little bit undersized, and therefore not super stable on its own, but makes it a prime target for future decays, or in the case of stars, nuclear fusions. In this particular case, other forms of beta decay would not make sense. So just as a consequence here, if I went through a positron emission with this, I would end up having 3 nothings. So I would rewrite that as this would be 3 neutrons. So a beta decay would basically disintegrate this nucleus into nothing if it was positron emission. So because of that, we're going to generally assume that this is not the one that happened, and rather it was the negatron beta decay that took place instead. All right, try these ones for yourself then. In this case, I have given you the parent and daughter nuclei. Try to figure out what kind of decay took place in each of these circumstances. So take a couple of minutes and see if you can figure it out here yourself. All right, let's see how we did. So the key to these kinds of problems, especially if we're not given the atomic numbers, is I usually try to put the atomic numbers in myself just so that I kind of have a something to base off of. So AC actinium is number element number 89, and francium is number 87. And so when I do that, I see, okay, we're 4 different on the top and we're 2 different on the bottom. And so I can approach this one of 2 ways. With these numbers, it would be absolutely correct to call this helium. Would not be wrong in the slightest. Additionally, you could recognize this as the alpha particle. And so the alpha particle, lowercase letter alpha, basically fish symbol. For vanadium is number 23, and titanium is number 22. And so we can see there's no difference in mass. There is a -1 difference in charge. And so you could write this in as beta, or you could write this in as electron. The process here would be called electron capture. The first one was, of course, alpha decay. Right. Any questions about transmutation reactions coming out of this section of the chapter? All right, let's go ahead and take a break then. Come back at 9:15.